And with those ones and zeros, that's actually a really key point about most industrial control system protocols, is that they don't give you any context over the wire about how those values map to the process. They're just sort of opaque ones and zeros or values or numbers, okay? All that context for saying, that this bit at this position in the message represents whether a valve is open or closed, and this number here happens to be a voltage, that's not actually contained in the protocol over the wire. That's usually information that's stored, either in the communication server that's talking to all these components, or, in an engineering workstation. And that's really important to understand for, protecting these systems from an attacker. Attacker typically has to do quite a bit of reconnaissance to be able to sort of map what's in the protocol to accomplish whatever their objective has to be. As applied to protocols, what that means is that these protocols were designed without any cryptographic security. Okay, and I say cryptographic because just putting usernames and passwords and then sending them in clear text over the network doesn't count. That's not security that's going to prevent an attacker who has network access from compromising things. And I won't go harp on too many of these bullets too much because Dale already mentioned frequently the easiest way to exploit a single device, not necessarily the whole process, but a single device, is just to read the manual and see what the protocol is capable of doing. Insecure by implementation. And I think I'll just skip to the bottom and say that the bugs that matter are the ones that allow you to do something important to the process that you couldn't already do through the protocol itself. And I'll give some examples of that on the next slide. There were quite a few bugs in the SCADA masters themselves. You could send malformed or intentionally malformed packets from the field back up to the master and crash the master system. That's important because, in a perfect world, if you've done that network segmentation that Dale talked about where site A can't talk to site B and you have everything locked down and only those protocols are allowed, if there's a bug in the master, you can just pretend to be that field asset and crash the system. And for particularly some of those bad bugs might allow remote code injection, where you could actually get into the control center or run malicious code on the control center by exploiting a bug in the protocol master. So I think sort of the last level of defense in depth is going to be adding security to the protocols themselves, where you actually sort of use cryptography to put private keys on the equipment and on the things that want to talk to them. And there's various ways of doing that we can't get into in this session, but I'd say that's sort of the final frontier and the final layer of defense in depth for network security. It's pretty unacceptable that the security you add, would result in affecting the availability of your control system. That would be a deal breaker for most people. And I think this is where people kind of thinking about protocol security really need to focus their attention over the next couple of years, is how do we add security to these protocols without affecting availability and making asset owners confident that that's really truly going to be the case.